All right, so today our main goal was to describe sequence convergence, and I thought you all did a great job, and I was really happy with the definition that we came up with and the way we were able to use it. If this isn't natural to you and it takes a little bit of effort, consider yourself normal. As I told you in class, it took the mathematical community 200 years to really figure out the ideas that we're talking about today in class. So don't feel upset, but just keep working at it. I know you'll get there. I know you'll be just fine. What I'm going to do in this video is just kind of re-say some of the things you said in class. I just want to emphasize a few points just to kind of keep us point out some things about the definition that I think are really important, and then introduce tomorrow's task. We have one more kind of reinvention task to do this week, and then we're going to move on Thursday, and then next week we'll move to the textbook and start doing things that are a little more textbook related. Some of you will like that better, and some of you won't, so it'll depend on your personality. But first, let's come back and think more about sequence convergence. And really, there were three ideas to sequence convergence, but before I write those down, let's just draw ourselves a graph, because I always have a graph of a sequence that we're dealing with. And the one that really was prominent today in class was this graph, what we called the dying sine graph. And so this graph that kind of was a sine graph that got progressively smaller as we went. So here's our dying sine graph, and really there were three key ideas that took place when we talked about this dying sine graph. The first key idea was this idea of boundedness, and that really is just the idea that we can bound this graph by different amounts. So we can bound the graph above and below by, say, this value right here. Say we can bound it above by 1 and below by -1. We could also try to bound it by smaller amounts. So instead, we could bound it by 1/2 and -1/2. And so, or we could even bound it by even smaller amounts. And so you'll notice we can just kind of keep bounding it by smaller and smaller and smaller amounts. And so the real idea in this problem was that we had this boundedness idea, and that is that what we're trying to do is we're trying to capture the changes in the graph. We're trying to capture how much the graph is changing top to bottom as we move all the way through it. And notice that this 1 and -1 bound, it captures the entire graph. But the 1/2 -1/2 bound isn't good enough, because there's still a bunch of points, most notably this point right here and this point right here, that aren't within that 1/2 -1/2 point. So that one's not good enough to do it. And then, of course, the closer one, let's just call that like 0.25. The 0.25 one, there are points all the way down here that aren't within the 0.225 graph. So the first big idea is boundedness. And boundedness is really nice, because how do you capture something is bounded? Well, this was from yesterday's class. Something is bounded if the absolute value of the sequence is less than whatever that bound value is. And I'll just put an M, and then we'll come and change that in a minute. Well, once we had boundedness, we had the second big idea, which is, I'm going to erase that. Once we had the boundedness, we had the second big idea, which you all jumped on really quickly, which is the idea that we have not just boundedness, but we have a starting value. And this is really related closely to this idea of eventually bounded. So if I look at this graph, these orange line right here, well, this orange line, it is not bounded by the orange line, but it is eventually bounded by the orange line. And what we mean by that is that we can come find some point on our graph, most notably about right here, where if we move to the right of this point, everywhere within the right, the sequence always stays within our values. However, before that starting point, it doesn't matter. So what we say is that to have convergence, we have boundedness, But we also have some starting point where it's bounded after some given point on the graph. So what happens at the beginning doesn't matter. And so when we try to capture this, what we really have is we have that there exists a capital N such that our function is bounded by our m and our negative m. And we've got these absolute values that we kind of talked about yesterday when we talked about boundedness. One of the conversations today is about this n. This n doesn't necessarily have to be an integer, although it often is if it fits nice and neatly on one of these dots. But sometimes the n, if it really doesn't matter where it is, as long as it's somewhere on the real line. Okay, finally, we've got one more thing to get to, and that is that being bounded isn't enough. It has to be bounded by every possible bound you could ever create. And this is the last big idea. And so the last big idea that we come across, which is kind of what I was trying to get at earlier when I was drawing these pictures, when I was drawing all those bounds earlier, is the idea of arbitrary closeness. So what do we mean by arbitrary closeness? Well, what we mean is that it has to be bounded. We have to have a starting value, but bounded by what? Well, we have to be bounded by any amount that you possibly can choose. So if I want to be really particular and I want to pick some value that's just like barely bigger and barely smaller than my x-axis. So say a number like 0.00001 and negative 0.00001. So suppose those are my two values, and I know my writing isn't very good here, but you guys can hear me and you can stick around. So if I pick just some really super small bound, some really close bound, then it doesn't matter how close I make it. If I eventually, so I can choose this however close I want, I can eventually get to a point where it becomes within that arbitrary close value. So it becomes bounded. So I pick some really small value. Once I pick the small value, then I can find a starting value. And once I find the starting value, after that point, it is bounded. So I drew these in key ideas 1, 2, and 3, but in some ways, the ideas almost work backwards, that we start by choosing the close value, and then you choose the starting value, and then you choose the boundedness. And there's a game that people kind of classically talk about. Now, first, it's not a game like a fun game, but it's kind of a way of illustrating what we mean by this experience. And that is that if a sequence converges, you could have two people, and person number one could give person number one could give them any number, and then person number two could pick the starting value that then bounds your sequence thereafter. If you played the game backwards, it wouldn't work. If person number one gave the starting value, you could always find some boundary that doesn't work. But what happens is you start with the close value, so you have to get so the first person chooses any number they want. Pick any number as small as you want. Person number two then says, oh, okay, now that you've given me that number, I can choose my starting value sufficiently large so that my function fits within that amount. So person number one says 1/1 billionth. And person number two says, okay, to get to 1/1 billionth, we have to go all the way out and start at capital N equals 1 million. And they go, oh, wow, okay, well, let's go with 1/1,000,000,000th. And the person number two says, well, if I wanted to start at 1,000,000,000,000, then I would have to get all the way for capital N to be 1/1 billionth. And so this game goes on and on. But as long as person two can always find an answer for person one, then we consider that the sequence is convergent. And so that gives us our definition as we wrote it. And our definition was for all epsilon greater than 0, there exists a capital N, and I'm not going to say whether it's a natural number or not, such that if N is greater than that capital N value, then the absolute value of A of N is less than epsilon. And so this is our really good definition for the definition of A of n converges to the number 0. Okay, so again, what I want to point out is that we have all the pieces of our different graph here. We have all the different pieces here. We have our boundedness kind of showing up right here, bounded. We have our starting point right here. And then we have the arbitrary closeness. Okay. And then as you look through these, what you'll see is that they follow kind of the pattern that I told you. You start with arbitrary closeness, and then once you pick that arbitrary close value, then the next job is to find which starting value goes with that close value. And then once you have that starting value, you then pick the bounded value. And this kind of comes then to the next thing that I really want to talk about, and that is how do we make proofs out of these things. And I gave this proof framework in class, but I think it's worth saying again. And this proof framework, this isn't magic. This is just meant to kind of be a guide for us as we go through the proof. So if we're trying to prove that some sequence an converges to 0, then all we have to do is we fill out this proof framework, but the proof framework is just this definition just systematically written down. So that first definition, we want to prove something's true for all epsilon greater than 0. So the very first thing we're going to write down is let epsilon be greater than 0. Okay. The next thing that we want to do is we want to show that if capital N is greater than n, then the absolute value is less than epsilon. So our next part is we're going to say let little n be greater than capital N. And then our final part is going to be therefore the absolute value of A of n is less than epsilon. And notice that if we have these 3 steps, we've successfully done our proof. And then inside here, this part of the proof is where we find, and instead of saying find, what if I just I'll write the word let again. We let capital N equal some number. And this first part is where we have to figure out what n is. This usually is some number that is a function of epsilon. So this usually has epsilon in it. Now, sometimes it doesn't, because sometimes we're dealing with a theorem where you have 2 sequences related to each other. And so that n may be the n that works for the previous sequence. And so if we have a sequence an and a sequence bn, then maybe we take the n from sequence an to prove something about the sequence for bn. But that being said, even in that case, the epsilon is still in there. It's just hidden in the language that we see. So this usually has an epsilon in it. Okay, and now we let n be greater than n, and then the last thing, and then this part, what we do is we do some sort of, this second step is usually some sort of algebra. And that algebra kind of lets us go from n being greater than capital N to this A of n being less than epsilon. And that just depends on our problem and depends on how everything works. But this proof framework works for all of our theorems. Okay, now once we have kind of the proof framework set up, we were ready today to talk about the second question. And the second big question is, what if it converges to something other than 0? What if it converges to some number L? And you'll notice if I look at my problem, well, everything is staying just about the same, except right here, this bar no longer represents 0. This bar now represents L, and 0 is somewhere else on the graph, either above it, below it. And so now these 2 little orange values, this is no longer the value 0.0001, or epsilon if I want to say it. This is now the value L plus epsilon, and this is now the value L minus epsilon. So what we're really doing is, instead of trapping the value between epsilon and negative epsilon, we're trapping it between plus and minus epsilon. But we still have these bounded idea going on. We still have this kind of strip in which we're trying to capture our sequence values, we let the strip be arbitrarily small. So we take that arbitrary closeness, so this part stays the same. We pick our starting point, and so this part stays the same. And then the only difference to the definition is how we go about bounding it. And we just changed this bounded definition ever so slightly. And we did this today in class, but let's go ahead and write it out one more time. And that was an minus L is less than epsilon. Where did that come from? That just comes from doing a little bit of algebra by noticing that if L minus epsilon is less than our sequence is less than L plus epsilon, then notice you could subtract L from everything, and we could get negative epsilon is less than an minus L is less than a positive epsilon, which is the exact same thing as writing this, this absolute value expression. You could also think of this an minus L as just taking your entire sequence, and if you subtracted L from your sequence, then that would just shift the sequence down to where you're at 0. So it would kind of move everything down to 0. But okay, and then once we've done this, our proof stays the exact same. Everything works out the exact same in our proof. The only real difference is down here. Our final theorem, instead of having an being less than epsilon, our final theorem is an minus L is less than epsilon. One quick point that this finding this n, so this part often seems a little mysterious, this finding the n equal to number, and this usually involves scratch work. So often we have kind of over on the side somewhere, you know, so often we'll have over on the side, we'll have some scratch work. And that scratch work is what's necessary where we solve for whatever our capital N value is. So we often will do that work on the side, but we don't actually include it in our proof. We just write down what N is with our epsilons. Okay, this was just meant to remind us of the conversation. What I'm trying to do is just kind of give us a big view, an overview of what we talked about today, just to clarify a few things. What should you take from today? If this definition that we have right here, this definition on the bottom, and now I've got so many colors that this whole place is going crazy. If this definition makes sense and you feel like, okay, I understand it, I know where all the pieces come from, it really seems like I believe it's the right definition. And then if you can say, okay, I can write a proof with this definition by following the basic structure of the framework. So I can write a proof by taking an arbitrary epsilon, finding my n, and then doing some algebra. If you feel like that definition makes sense and you can write proofs on it, you are exactly where I want you to be in the class. If you're still finding that difficult, again, this is normal, but just keep working on it. So don't quit right now. Just keep working on it. Okay, we have one more layer to add to all of this, and the last layer is a limit. And so now, instead of talking about sequences, which is what we've been talking about the last few days, we're going to move from sequences to functions. And so functions of a real number. And so as we move from sequences to functions, instead of having a graph like we've had with a bunch of dots on it, we're going to have traditional graphs that look more like calculus type problems, or algebra type graphs. So we want to move from sequences to functions. So one thing you need to try to do is remember a little bit of your calculus class. And so from calculus class, we want to ask ourselves, what does a limit mean in calculus class? So what is the limit as, say, x approaches 2 of f of x equals 5? And you probably remember this, but just as a quick summary, what this is saying is it's saying something about the value at x equals 2 and y equals 5. And so something about the graph is kind of approaching that value nearby. So if you remember these, we have to kind of look close to this value, look on the left and look on the right, and see if we can make sense of it. Okay, so our goal for the day is to do the exact same thing we did with sequences, but do it with functions. So I want you to create graphs of as many, so we're going to do graphs. I want both examples and non-examples. So take graphs of as many qualitatively different examples and non-examples as possible of functions with the limit as x approaches 2 of f of x equal to 5. And then try to finish this definition, the limit as x approaches 2 of f of x equals 5 if, and write this out. How will you know your definition is good? Well, it's hard to know, but don't try to use vague words. Don't be using words like it gets really close to or approaches or things like that. Instead, try to use very precise things that we can calculate. So notice our sequence definition, what I really like about it is that these are all very precise statements. For all epsilon, there exists an n such that a of n minus L is less than epsilon. These are all very precise things that we can do math with. This is much more precise than saying as n gets big, the values kind of get close to L, right? That's not a very precise statement. These statements using quantifiers and inequalities are the things that we can then tackle and use math and do proofs with. So you'll know you're on the right track if you've got a proof that kind of feels, a definition that kind of feels similar to the things we've been doing and is using quantifiers and inequalities kind of in the ways that we've been dealing with it. Okay, so try to come up with your definition of a limit and try to come up with your examples and non-examples, and I will see you in class. One last thing you might consider, we will talk about this just briefly. Maybe I'll touch it tomorrow. More likely we'll come to it later in the semester. Is once you've done the limit of a function, you can ask yourself, what would happen if we had more than one variable? What if we had like a 2-variable or 3-variable function? What would that look like? And that's a fun, separate question. Again, I think we'll probably come to that maybe the last week or two of class. All right, I'm going to enjoy seeing you in class tomorrow. One thing I really want to point out is I want to just kind of make sure that you guys are doing this and staying on top of these tasks. You all have been really good so far, but please just go ahead and put your responses in the Dropbox before you come to class, just so I can see that you've thought about it and you've written some things down and you have some contributions to make to the conversation. You don't have to be right. I'm not going to be grading on correct and incorrect. I'm just grading it on did you spend some real quality time thinking about the task before we show up for class. That's an important part of class. And also, make sure you're getting your homework in that Dropbox. If for any reason you have trouble with the Dropbox, you can email me as well. Okay, so once I kind of pretty soon I'll be able to start going through this homework. So I'm gonna be able to get a little bit of grades put together and then get some responses to you all on the things that went well or didn't go well with the homework. And hopefully I can get on top of that before this first take-home test comes out on Thursday. So I've enjoyed the first 2 days of class, and I will see you all tomorrow.